Hello everyone, this is Physics 103. This lesson is on atomic structure. So this is a continuation of Bohr's model of the hydrogen atom, and we will be discussing how the energy is quantized inside the hydrogen atom. So recall previously that we have quantized angular momentum of an electron as well as its orbits in terms of r inside the hydrogen atom. Now we ask if, for example, we apply an energy in the form of light in the hydrogen atom, how does its energy transition from one state to another state? So for example, our electron is in a state of n equals 1. So it's orbiting at this radius of n equals 1. And then we shine a light, we give an energy hf to the electron, and then that electron will accept the energy only in quantized amounts. So what is that value of energy for it to transition for example, at n equals 1 to n equals 2 or to n equals 3. So we are interested in determining first the total energy of the electron. So we know that classically we have defined total energy to be the sum of kinetic energy and potential energy. So if we determine the kinetic energy and the potential energy, we would know how the energy is being quantized inside a hydrogen atom. Okay, so first we find what is the kinetic energy. So we know classically that this is 1/2 times m times v square. Okay, so for potential energy, since we are bound inside the Coulombic potential, we know that the potential energy should have the potential energy of electrostatic potential. So later on we will see what is that electrostatic potential. So first let's look at what is the kinetic energy. So recall from our classical model using Newton's laws, we solve for the radius. Actually, we can also solve for the velocity of the particle, or in this case, our electron inside the hydrogen atom. So our v is given by 1 over epsilon naught e square over 2 h. So please take note that we transition now from h bar to h because it is more simpler if we write the energy in terms of h in this case. Okay, so this is the velocity of the electron. Also, this n term appears, so we know that the velocity is quantized. So when we write the kinetic energy being 1/2 m v squared, we get that Ke will be 1 over E naught square times m e to the 4 8 n square h square. Okay, so this is our kinetic energy. Okay, so now what about the potential energy? So for our potential energy, this is given by negative 1 over 4 pi epsilon naught E square over the radius R. So now we note that this negative sign is chosen because we have taken the electric potential energy to be 0 when the electron is infinitely far from the atom. So this doesn't affect much our calculations because we are interested in changes in energy. So we are more interested in the changes in energies. Okay, so our R here, we have also already solved this. This is in terms of H, not in H bar, we have R equals E naught N square H square over pi M E square. Okay, so writing our potential energy with R, we have negative 1 over E naught square times M e to the 4n square H square. So this is our potential energy. Okay, now we can get the total energy. So kinetic plus potential. Note that we have same terms. So this is 8, right? This is 1 over epsilon naught square m e to the 4 n squared over h squared. This also has e naught square m e to the 4 n square and h square. So we can factor out the like terms and we can write this as simply as 1/8 minus 1/4 times this constants. 8 n square h square. Okay, so 1/8 minus 1/4 gives us negative 1/8. So we would have minus, let me factor out n square, and we would have m e to the 4 over 8 epsilon naught h square. Now, if we try to simplify all these constants in this term, we would see that our energy can be expressed by 1 over n square times negative 13.6 electron volts. So this is our result.